Hi folks, welcome back to my channel Simony. Today we are going to cover dynamics and let's begin with the topic Newton's laws, right? So Newton's laws are the foundation for the classical mechanics. We can apply these laws anywhere we want. Almost, the civil engineering and mechanical engineering, they will highly use these simple laws. Okay, right. So first of all, let us discuss what is a force. Force is the quantity which can change the velocity of an object. Now, Newton's first law defines what is force and what is inertia. Okay, right. So see, change in velocity means maybe the force will change the magnitude or it can change the direction. Okay, right. Now, let's say you are a bus. You are traveling in a bus and you are sitting in a bench actually. And if the bus stops, what will happen? You will be moving forward, correct? So why is that? It's because when the bus is moving with a constant velocity, both you and the bus are in the inertial state. Now, when the bus suddenly stops, what happens is your lower body, which is in contact with the bus, will become non inertial. That means your lower body will stop. However, your upper body will continue its state of uniform motion. Good? Right. Now, same thing happen when a bus at rest start suddenly. Then what will happen? If it is traveling with a high acceleration, then you will move backward because your upper body is in the rest state. Now your lower body is in the non-inertial state. Now what is this inertia? Inertia literal meaning is laziness. Okay, right. So we are in a state of laziness until an external force acts on it. If you are in the bus and if the bus suddenly start, your upper body is in the inertial state of rest action. Okay. Now, how the inertia is related to a body? More the mass of the body, more the mass of the body means more will be the inertia. It will be difficult to change the state of it. Good, right. Now, the Newton's first law says that every object continues its state of rest or uniform motion until an external force acts on it. Okay, so force is required to change the state of an object. That is the meaning of it. Good. Now, what is inertia? It's a property associated with a body by which it continues state of rest or state of uniform motion in the absence of force. Good. Right. Now let's focus on Newton's second law. What does it say? It states that rate of change of linear momentum of a body is directly proportional to the force acting on the object. Now, first of all, what is linear momentum? Linear momentum is defined as mass into velocity, and of course, it is a vector. Okay, right. So Newton's second law says that the force is directly proportional to rate of change of linear momentum. So how to find the rate of change of the momentum? See, rate of change means you first find the change in momentum that I have written here, delta P equal to Pf minus Pi, where Pf is final linear momentum and Pi is initial linear momentum, and that you can find by just mass into final velocity and mass into initial velocity respectively, right? And the rate of change of linear momentum means you had to divide delta P with time duration. So that's what written here, delta P divided by delta T. Now you may think, what is this delta represent? Delta is an operator for change. Okay, right. Now that equation, that proportionality, we can convert into an equation, F is equal to K into delta P by delta T, where K is a constant. So F is equal to del P by del T. Suddenly, how you may think, what happened to the K? K in SI unity is taken as 1. Okay, right. Now, if you substitute the expression for Pi and Pf in the change of delta P, you will get F is equal to m into Vf minus mvi divided by delta T, which is equal to m into Vf minus Vi divided by delta T. Now, Vf minus Vi is nothing but change in velocity divided by time, we know, is acceleration, correct? So, force is equal to mass into acceleration. Remember, this is not the direct statement of Newton's second law, but this is a Newton second law result, just a result. Okay, actual equation for Newton's second law is this one. Now you may think why I'm saying this is not a general equation. The reason is this equation is only valid when mass is constant. When mass is constant. Okay, for example, if somebody is applying certain force on a box, the box will move with a certain acceleration, and we can find that using this formula. However, you cannot apply this formula for rockets where the mass is constantly changing, correct? Right. To understand the Newton's second law better, let's do an example. So example 1 is a child kicks a football with force 50 Newton with an impact time of 9 milliseconds. If football has a mass of 300 grams, find the speed of the football immediately after the kick. Good. So let's do that. You know, first of all, we have to identify what are the things given. Here, force is given as F is equal to 50 Newton and mass is given as 300 grams. We will write it as 0.3 kilogram because kilogram is the SI unit, right? Now, we have the impact time, which we can write delta T because time duration for that momentum change is nothing but this impact time, right? So delta T equal to 9 milliseconds, which we can write 9 into 10 to the power minus 3 seconds. Good. Right. Now what we had to find? The speed of the football. Definitely to find the speed, we had to find the acceleration. So acceleration, we can find it as A equal to force divided by mass, which is nothing but 50 divided by 0.3. All right. So that is the acceleration in meter per second square. Now acceleration, we know it is change in velocity by time. So Vf minus Vi divided by delta T equal to 50 divided by 0.3 meter per second square. Now the thing is, initial velocity is 0, okay, because we are kicking a football which is at rest. So Vf divided by delta T must be equal to 50 divided by 0.3. Therefore, Vf is equal to 50 divided by 0.3 into delta T, and we know delta T is 9 milliseconds or 9 into 10 to the power minus 3 seconds. So 50 divided by 0.3 into 9 into 10 to the power minus 3, which is equal to 50 into 9 divided by 0.3, we can write 30 times 10 to the power minus 3. So the final result will be nothing but, which is going to be 1.5 seconds. Now let's do a second example. A box of 15 kilogram is pushed by a force of 60 Newton. Find the acceleration of the box. Then second part is how far the box will move in 10 seconds starting from rest. So here I have provided the answer. You know, A equal to force by mass, which is 60 divided by 15. So that will be straight for 4 meter per second square, right? Now, since Vi equals 0, that means initial velocity is 0, and A equal to 4 meter per second square, and time is also given t equal to 10 seconds. Therefore, you can write, you can use the equation of motion to find delta x, which is equal to Vi t plus half into A into t square. So 0t plus half into 4 into 10 square. Why 0 here? Because initial velocity is 0, right? So if you cancel the 2, it will become 2 into 10 to the power 2. So finally the answer is 200 meter. Great. Good. Now comes Newton's third law. Newton's third law Now comes Newton's third law, and it states that for any action, there is an equal and opposite reaction, right? So the two forces acting on two bodies. Remember, the two forces are acting on two different bodies, all right? Now, what are the examples? What are the examples? One of the very good example is rocket propulsion. The rocket is actually pushing the gases downward with an action, and the gas is pushing the rocket upward, which is a reaction. Good. And when you are walking, you are pushing the floor backward using friction, and the floor will be pushing you forward. So your push is action, and the floor pushing you is the reaction, right? And if you hit the wall is also hitting you. That's why you are feeling the pain, right? So that's also action reaction pair. There are plenty of examples. Okay, right. Now let's consider a general two bodies, A and B. They are colliding each other basically. Therefore, the force acting on B due to A, we can represent FAB, and according to Newton's second law, that must be MB into AB, mass into acceleration, right? Now, similarly, now the force due to B on A is given by FBA equal to MA into A, right? Now, according to Newton's third law, these two forces must be equal. That means MA into AA equal to MB into AB. So, if you rewrite, you can see that AB by AA equal to MA by MB. Let's say if MA is less than MB, then this term will be less than 1. So what is the meaning of it? AB by AA will be less than 1, and that means AB is less than AA. That means suppose a heavier mass is colliding with a lighter mass, then the lighter mass will be accelerating more, and that makes sense, right? If the truck is colliding with the car, the more acceleration will be for the car, correct? Good. For value addition, I'm giving an example. Suppose you are climbing on the land from a boat. So, in order to move forward, you had to push your leg backward. So, what will happen? Because of the action, the boat will be moving backward, and the boat will also be pushing you. Now, what will happen if there is no binding or if there is no rope that is tied with the boat? Now, if there is no connection with the land and the boat via a rope, then what will happen? The boat will go backward, and there is a high chance that you will be going straight down into water. So that's why always we use rope to bind the boat, right? Now let's do a question based on Newton's third law. A truck of mass 2000 kg collides a car of mass 800 kg with force 10 to the power 4 Newton. What is the acceleration of the car and the truck? So we are going to find the acceleration of the car and truck separately. Okay, right. Now, let me draw a very simple picture. There is a truck and it is colliding with a car. The force acted on the car by the truck is F A B equal to 10 to the power 4 Newton. And let me consider truck as A and car as B, right? Now the force acted on the truck by the car is nothing but FBA, and both of them must be equal actually. FBA must be equal to FAB, at least by magnitude, right? Good. Now we can therefore write MA into AA must be equal to MP into AB. Now that force is directly given 10 to the power 4, right? And therefore, the acceleration of the car, first of all, will be AB equal to 10 to the power 4 divided by mass of the car. So 10 to the power 4 divided by 800 kilogram, right? That will be 10,000 divided by 800. 0 cancels, so 100 divided by 8, which is definitely 12.5 meter per second square. Good. Right. Now for the truck, AA equal to similarly the force divided by mass of the truck. So that will be 10 to the power 4 divided by 2000. So that is straightforward. 10,000 divided by 2000, which is nothing but 5 meter per second square. You got it? Great. Now let's focus on free body diagrams. Now, why we use them? It is to apply Newton's second law so that we can find the acceleration. So it's a simplified diagram in which we can represent all the forces. So it is a representation of all the forces acting on an object or a system where we can identify the acceleration in different directions. Okay, right. Now, here is an example. An object at rest on a horizontal surface. What are the forces acting on it? You can see that definitely gravitational force is acting downward, which is W, which you can write mg, right? And there is a normal force also. Now you may think, what is normal force? Normal force is nothing but reaction force from a surface. Okay, that means here the action is gravity and reaction is the normal force, right? And not all the cases normal force will be equal to gravitational force, and we will see that. All right, so in this case only n is equals to mg. That means for horizontal cases, when the object is on the horizontal level, almost all the cases you will get n is equal to mg. But there are some cases in which normal force will be less than the gravitational force. We will see that. Okay, right. Now another example is, in this case, remember, the total force will be equal to 0. In this case, therefore, F net equal to 0, because both N and W will cancel out, right? Good. Now, another example is a box is pushed on a smooth surface with force Fa. In this case, even though N and W cancel out, you have an applied force in the positive x direction. Therefore, there will be a net force, and net force will be equal to Fa, and you can find the acceleration of the body by just using the Newton's second law, F net divided by mass, where m is the mass of the body. So that will be just applied force divided by mass. Great, nice. Now there is a third example here. An object is pushed with applied force on a rough surface. What is the specialty of the rough surface? Rough surface means you will have a friction in the opposite direction of the motion, right? So you can see that just opposite to the applied force, there is a friction Ff, and if the object is moving, then the friction is called kinetic friction, and if the object is at stationary, then the friction that come into play is static friction. So I will explain both of them in detail. Static friction is like when you are when the object is on the surface, you need certain force just to move the object. That maximum force is nothing but the static friction, and the static friction is proportional to the normal force. Experimentally, it is found that the static friction is proportional to normal force, and that proportionality you can convert it into an equation. Fs is equal to mu s into n, right? Now, since there is no acceleration in the y direction, we can write ns equals to w. So n minus w equal to 0, n minus mg equal to 0, right? Therefore, n must be equal to mg. Therefore, you can write the friction must be equal to Fs into mu s into normal force, which is mu s into mg. Now, also in the horizontal direction, in the stationary case, F applied must be equal to static force. That means Fa minus Fs is equal to 0. That's why the acceleration is 0. Okay, right. So in other words, Fa equal to mu s into mg. What is the meaning of this last equation? It means that your applied force must be at least slightly larger than mu s into mg to move the object. Good? Right. Now let's focus on the kinetic friction. This kinetic friction will be less than the static friction because of the inertia basically. Okay. Right. Now Fk is proportional to normal force, and Fk you can convert into an equation by introducing a constant mu k, which is known as coefficient of kinetic friction. I think I forgot to mention the name of this one. Mu s is nothing but coefficient of static friction. Good. Now in this case, of course, n is equals to mg because there is no motion in the vertical direction, and however in the horizontal direction there is a net force which is given by applied force minus the kinetic minus applied force minus kinetic friction, which is Fa minus mu k into mg, and according to Newton's second law, that must be equal to mass into acceleration, correct? So finally, acceleration will be equal to Fa minus mu s mg divided by m. Great, nice. Now let's focus on an example that consists the concept of friction. Good. Here is the question. A child pushes a box of mass 4 kg with a force 40 Newton on a rough surface. If the coefficient of friction is 0.5, what is the acceleration of the box? Now here, rough surface means that there is a friction. Okay. Definitely, the friction here is kinetic friction because there is a relative motion between the box and the ground, correct? Right. So of course, we had to start with the drawing of free body diagram, right? So let me draw a box, and it's on a rough surface. It is on a rough surface, right? Good. Now the coefficient of friction I can denote mu k equal to 0.5 here. Now clearly there are four forces acting on it. One is applied force, which is given in the question, 40 Newton, correct? And there is a normal force, N, which will be exactly equal to m into g, which is the weight. Now, why they are exactly equal? Because there is no acceleration in the y direction. Okay, so net force must be equal to 0. That's why n must be equal to mg magnitude wise. Direction wise, they are opposite. Basically, they are action reaction pairs. Okay, right. Now opposite to the applied force, there is a friction. So let me denote with Fk corresponding to kinetic friction. Okay, so first of all, we have derived Fk is equal to mu k into n, which is equal to mu k into mg, because n is equal to mg, right? Now we can substitute the values. Fk equal to 0.5 into mass is 4 kilogram into g is 9.8. This is clearly 4 into 4.9, which is equal to 19.6, correct? Yeah, Newton. Good. Right. Now the motion only is along the x direction, so let's focus on Newton's second law in the x direction. So F net x, that means net force in the x direction, is F applied minus Fk. Why it is minus Fk? Because the friction is acting in the negative x direction. Okay, right. So the net force along the x direction will be 40 minus 19.6, which is clearly 20.4 Newton. Now using this force, we can find the acceleration along the x direction, which is ax is equal to f net x divided by mass of the box. So that will be 20.4 divided by mass is nothing but 4, right? So that's clearly 5.1 meter per second square. Good. So that's the answer. So that's it, folks. We have discussed a lot on Newton's second law. In the next video, I'll be discussing about more problems based on the friction. Good. And related materials I have attached below as a link. Please go through it. So see you soon. Bye bye.